Thanks for the introduction and thanks for the invite. It's really, really great to be here. So the title of my talk is Expressibility and Trainability, Balancing the Ingredients of an Effective Quantum Neural Network. You'll notice this is slightly different to what I put in the original advert. I originally described it as balancing the ingredients of an effective variational quantum algorithm. But as I was preparing the talk, it became clear to me that much of what I have to say also applies to quantum machine learning methods, and I really wanted to emphasize that, hence the switch in terminology. And this is joint work with a whole host of others, predominantly at Alamos. Okay, so I'm going to try and cover quite a bit in this talk, so I thought I'd just give you an overview of my plan of attack before starting out. So I'm going to start off by pinning down two requirements for a quantum neural network, or QNN, to be effective. So these are expressibility and trainability. I'll spend quite a while pinning down exactly what I mean by expressibility and trainability and sharing some prior results on them. So hopefully my talk should be quite pedagogical. And then I'll get on to some of my own results. So the first of these will be a trade-off that we have proved, showing that you cannot have a QNN that is both highly expressible and trainable. And secondly, I'm going to share results that tells you you need to pick your target problems carefully. So specifically, we have shown that any attempt to learn scrambling unitaries or random unitaries using a quantum neural network is going to face serious trainability issues. Okay, but first things first, for the purpose of this talk, I am going to focus on any method that optimizes a quantum neural network, i.e. a parameterized quantum circuit. I'll use these terms pretty interchangeably, by minimizing a quantum cost, potentially using training data. So these methods encapsulate, I think, basically all variational quantum algorithms and some, but far from all, quantum machine learning methods. Okay, so let me just spell out in a bit more detail about how these methods work. Well, the idea is you're going to try and train a quantum neural network to minimize a problem-specific cost function. And you're going to pick your cost function and your quantum neural network such that if successfully trained, the optimal parameters you find, or your optimal circuit, or your optimal cost value are in some sense an approximate solution to whatever problem you're trying to solve. Okay, and well, how do you do your training? Well, you can do this using a hybrid quantum classical optimization loop. Okay, so how does this work? Well, you run your favorite optimization algorithm. So this could be sort of gradient-based method or Bayesian methods, or your favorite Python, SciPy, black box optimizer that, to be honest, you don't really understand how it works, but with your cost function evaluated on the quantum computer. So you tell the quantum computer to run some parameterized quantum circuit with respect to a particular set of parameters. You then perform some measurement, and that's going to be your cost function with respect to those particular parameters. That's fed through to the classical computer. The classical computer decides what parameters to try next. That's fed back through to the quantum computer, and you keep on minimizing around until you've minimized your cost. And as I said, your optimal solution will be, in some sense, a solution to your problem. Okay, so to make this a bit more concrete, I'm going to run through one example, which I think will be helpful to understand the first half of the talk, and be actually pretty critical to understand the second half. And that example is learning an unknown unitary. So the idea here is to find some optimized quantum circuit such that the optimized quantum circuit equals the target unitary. And how are you going to do this? You can do it by picking a cost function such that the unitary that minimizes it matches your target unitary. There's a number of different ways you can do that, but I'm going to spell out to you a sort of quantum machine learning type approach where you construct your cost using training data. And one possible set of training data could be a set of n input-output pairs where your input is some quantum state and your output is that quantum state evolved under your unknown target unitary. And then you can use this to construct a cost in many different ways, but the one I'm going to spell out is as follows. So you can construct a cost as just the average of 1 minus the distance between your output state, so that is your input state evolved under your target unitary, and your guess state, which is your input state evolved under your parameterized quantum circuit. And note this can be rewritten in terms of sort of 1 minus the average fidelity between your output state and your input state acted on by your parameterized quantum circuit. And that makes it straightforward to measure. So you've just got to prepare your input state evolve it under your target unitary, apply the inverse of your parameterized quantum circuit, and then perform a measurement, a sort of projected measurement back onto your input state. And then you just repeat this for all your different possible psi-i's. Okay, so that's one way you could go about trying to compile or learn an unknown target unitary by training a quantum neural network. But that's just one possible cost function. There are many other options, and just the core idea is to pick a cost function such that the unitary that minimizes it matches the target unitary. So for example, it was shown in these papers here that it's also possible to learn a target unitary just using a single initial entangled Bell state and a single Bell measurement. Okay, and that was just one example of why you might try and train a quantum neural network to solve an optimization problem. But there are many, as I'm sure, because it's QHack, you are all very aware, algorithms out there that involve training quantum neural networks to solve an optimization problem. But in order to get these algorithms to work, and also to help us come up with new, more exciting algorithms, we're going to need to know what is a good quantum neural network, and how to prepare them, how to structure them. So that's essentially what I'm going to be spelling out for the rest of the talk. What makes a good quantum neural network? Can we have sort of rigorous analytic results quantifying what makes a good quantum neural network? Okay, so before I do so, let me just take a step back and set out the framework I'm going to be considering. So the first thing you need for these kind of methods, okay, so just for concreteness, I'm going to consider cost functions of this form, where you've just got some initial state, you evolve it under some parameterized quantum circuit, and then you perform some measurement. So in this straightforward form, this type of cost doesn't necessarily allow us to capture costs involving methods involving training data, but you can allow for training data essentially just by introducing a sum over I at the front and a subscript I here and a subscript I there. And all the results in the papers I'm presenting to you generalize to this case, and we show that in those papers. So I'm just really considering these simple costs for this talk so I can simplify the equations on the slides. Okay, so focusing at least for this talk on simple costs of this one. And then the first thing we need for these kind of methods to be successful is you need to pick your cost function such that it is faithful. So that is, you need the unitary that minimizes the cost to be in the set of approximate solutions to your problem. I say set of solutions because it could be more than one solution. I say a set of approximate solutions because often it's too stringent to demand that you find the exact solution. So for example, for learning some target unitary, this set is just going to be the set of unitaries that well approximate your target. Okay, so once you've got your cost function, the next thing you need to do is you need to pick an ansatz for your parameterized quantum circuit, or your QNN. And while discrete parameterizations are possible, typically your parameters will be rotation angles of some form. And typically we can write our parameterized quantum circuit in this form as consisting of a product of fixed gates and parameterized rotations. So the fixed gates can be anything really. On the left here, they're just sketched as ladders of ZZ gates. And the parameters rotations, these are going to be unitaries of this form, so e to the minus I theta j vj, where your vj's are Hermitian and vj squared equals identity. So for example, vj's could be Pauli operators or products of Pauli operators. On the left here, I've just sketched them as single qubit Pauli rotations, so your vj would just be a single qubit Pauli operator. But in general, these could be highly entangling gates if you fancied it. And note this is really a pretty general structure for an ansatz. So even though I've not done it this way here, your WJs and UJs could vary from there to there. The only restriction I'm going to impose for now is I'm going to assume that each of these sort of theta rotation angles vary independently, so there aren't correlations. Right, okay, so once you picked your ansatz, then given a particular set of input parameters, so theta1 here is a vector of all of these different angles, you have a corresponding output unitary. So a circuit that's actually implemented. Therefore, given a set of different possible input parameters, you have a corresponding set of possible output unitaries. And I'll call this set of output unitaries the set of unitaries accessible by the ansatz. Okay, so in order for QNN to be successful for solving a particular problem, we need a solution unitary to be captured by the ansatz. So that is, we need the set of unitaries accessible by your ansatz and the set of approximate solutions to whatever your problem is. We need the intersection of these two things to be non-empty. When this condition is satisfied, the ansatz is said to be complete. So we sketch this on the bottom here. So the grey oval represents the total space of unitaries. The blue oval is going to be the set of accessible unitaries for the ansatz that you're proposing to use. And the green and red blobs are solutions, the sort of set of solutions to two different problems, problems A and problem B. So this ansatz contains a solution to problem A, but not problem B. Accordingly, it's complete with respect to problem A, but not problem B. You could use it to solve problem A, but you'd be pretty screwed if you tried to use it to solve problem B. Okay. So in the absence of prior knowledge about where your set of solutions lies, or if you want to come up with an ansatz that's going to work for a wide class of problems, your best bet is going to be to use an ansatz that explores the space of unitaries as fully and as uniformly as possible. And such ansatz are known as expressive ansatz. So the ansatz I showed you before is pretty inexpressive. This blue blob is much smaller than the grey blob. It doesn't explore the total space of unitaries very well, and therefore we found, yes, it contains a solution to problem A and not problem B. One on the right, on the other hand, is highly expressive. So it explores the total space pretty well and correspondingly contains solutions to both problems A and problem B. Okay. So that's a pictorial representation of expressibility. It can be pinned down more mathematically by comparing the ensemble of unitaries accessible by the ansatz to the maximally expressive uniform distribution of unitaries. So that is the hard distribution. And we can do that by introducing the following expressibility super operator. So this super operator here is just the t-fold channel induced by the hard distribution minus the t-fold channel induced by the ensemble of unitaries accessible by the ansatz. Because this is going to come up later, let me just introduce the concept of a t-design now. So an ansatz, a ensemble of unitaries is said to form a t-design if a of x equals 0 for all operators x. So that is an ensemble of unitaries looks is a t-design if it agrees with the hard distribution up to the tth moment. Or more loosely, it's an ensemble that looks random when considering at most only t copies of the unitaries in the distributed copies of the unitaries within your ensemble view. It's annoying how you can't that we don't have a sort of way of, they're both U. I mean, okay, so I meant U and then sort of math BBU. It'd be good to have language to distinguish between these different U's. I get sidetracked. What was I saying? Okay, so in many cases, we're only going to be interested in at most the twofold channel. We only need to consider these things up to the second moment. So for that reason, I'm going to drop the t subscript and replace it with 2. And I no longer bother the t subscript here. And now we have that if a of x equals 0 for all x, then our ensemble forms a 2 design. Okay, back to expressibility. Remember, we are interested in minimizing cost functions of this form. So that is, you have some initial state psi, you evolve it under your ansatz, and then you perform some measurement operator h. Okay, so that means we are interested in the expressibility of our ansatz with respect to our initial state psi and our measurement operator h. That is, we're interested in the norm of the expressibility super operator when acting on our measurement operator h or our initial state psi. So rho here is just the density operator associated with our state psi. Okay, so if these expressibility measures epsilon rho and epsilon h are small, that means the left-hand side minus the right-hand side here is roughly small. So the blue oval well aligns with the grey oval. We're dealing with an ansatz that is highly expressive. But if these terms are large, then there's a large difference between these two sides, big difference between the sides of these two ovals, and we're dealing with an ansatz that is highly inexpressive. So in this way, these quantities give us a formal way of quantifying how expressible our ansatz is, but they do so in a way that is especially tailored towards our choice and cost function. So it depends on what we're interested in measuring and what state the circuit's initially in. Okay, so that's expressibility. But just because an ansatz contains a solution doesn't mean you're necessarily going to be able to find it. It's like an Easter egg hunt. Just because you're looking in the right room doesn't mean you're necessarily finding the eggs. And in the context of minimizing cost function, well, what we also need is we need the cost landscape to be sufficiently featured to enable training. So I'm now going to sort of hone in slightly on gradient-based methods, but much of what I have to say equally applies to other methods. So if you're trying to employ gradient descent, a good way of thinking about this is to imagine that you're stuck on a mountain trying to find your way down, but it's foggy and you don't have a map and you're a bit of an idiot. Well, one of your best bets to get down safely is just going to be to follow the steepest route down at any moment in time, which is roughly what water does, which is why sort of my red stick figure here is going to probably follow the stream back down to safety. But this is only going to work if you can figure out which is the steepest route down at any moment in time. So this little man here is not going to be able to figure out which is the steepest way to go at any moment in time, unless he uses very precise measurements. More on that in a second. So in effect, he's going to probably end up in a random walk and have absolutely no luck finding the lowest point on this field here. Okay, now this is especially an issue in the context of minimizing quantum cost, because if you have small gradients, then you're going to need very, very high precision measurements to try and figure out which is the cost minimizing direction. And now in the context of measuring a quantum cost, if you want a quantum cost to high precision, you're going to need to run your circuit many, many times because you only ever get your cost statistically. So more precisely, 1 over sigma squared shots are required to estimate a cost to precision sigma. So if you've got small gradients, you're going to need very, many, many shots. So it's going to be resource intensive. Okay. So how do we know if our landscape is a nice and textured and featured one that's going to allow for training, or whether it is impossibly fat and untrainable? Well, the way to assess the trainability of a quantum neural network is to study its expected cost gradients. So that is the partial derivative of the cost with respect to each of the rotation parameters. Okay, now for typical ansatz set of the sort of type I showed earlier, it's pretty straightforward to show that the average partial derivative of the cost vanishes. So that is, the cost landscape is unbiased. You're equally likely to come across positive gradients and negative gradients. But just because your cost landscape is unbiased doesn't tell you whether or not it's trainable or untrainable. So both of these landscapes are unbiased. The one on the bottom clearly isn't trainable. The one on the top hopefully is. So to assess the trainability, it's helpful to call Chebyshev inequality. So Chebyshev's inequality bounds the probability that the partial derivative of the cost is greater than some amount delta in terms of the variance in the partial derivative of the cost over delta squared. So if the partial derivative, the variance of the partial derivative of the cost is small for all parameters, then the probability that the partial derivative of the cost is non-negligible is also going to be very, very small. So that is, small variance entails small cost gradients. Right, okay, so the first person to investigate, well, the first group to investigate the trainability of quantum neural networks was Jared McLean et al. In this paper here. I think Jared's actually on straight after me. And what they showed is that if your ansatz forms a 2 design, so that is, if it agrees with the hard distribution up to the second moment, then the variance in the partial derivative of the cost vanishes exponentially. So combining this with Chebyshev inequality, what you're going to get is the probability of observing non-zero gradients is going to vanish exponentially with problem size. And so the number of shots required for training grows exponentially with problem size. By problem size here, I mean the number of qubits defined with respect to. So n here is just the number of qubits. And this means that for small scale problems, your landscape may be sufficiently featured to enable training. But for large scale problems, your landscape is going to become overwhelmingly flat, and training is going to become next to impossible, too resource intensive. And this is known as the barren phenomenon. Okay. So what I want to highlight to you is that this result can be reinterpreted using the notion of expressibility I introduced earlier. So ansatsa form two designs. Those that match the hard distribution up to the second moment are perfectly expressive ansatsa, i.e. they are ansatsa that explore effectively fully explore the space of unitaries, at least up to the second moment. And so what this result shows is that perfectly expressive ansatsa are untrainable. They will exhibit barren plateaus. Okay, but now the converse isn't true. And this was shown by my colleague Marco, who spoke on Monday, kindly swapped slots with me, and some of my other colleagues at Lanham. And what they showed is that global costs, i.e. those where the measurement operator acts non-trivially on all qubits, exhibit barren plateaus at all QNN depths, all ansatz depths, including constant depth. Now, a short, say, single layer ansatz clearly isn't very expressive. In fact, it's going to be highly, highly inexpressive. And so this shows that inexpressive ansatsa can also be untrainable. Okay, so we have the perfectly expressive ansatsa are untrainable, and inexpressive ansatsa can also be untrainable. They're not always trainable. Can we formalize this trade-off? Okay, and that's precisely what we do. That's the first result I want to share with you. So we have derived an upper bound on the variance in cost gradients in terms of their expressibilities. So in terms of the expressibility measures that I introduced earlier. This is what we get out. So on the left-hand side here, we have the variance of the gradient of the cost for an arbitrary layered ansatz of the form I showed earlier. And on the right, the first term is just the variance in the gradient of the cost for a maximally expressive ansatz. As I argued earlier, Gerard McLean showed that this vanished exponentially with the size of the problem. And then the important part is these two terms. And actually their exact form isn't really that important, but what matters is that they increase with the expressibility measures epsilon rho and epsilon h. That is, they increase with increasing inexpressibility, or conversely, they decrease with increasing expressibility. So what we find is that the higher the expressibility of the ansatz, so that is the smaller epsilon h and epsilon rho, the smaller the upper bound on the variance in the partial derivative of the cost. So that is, highly expressive ansatsa will have flatter landscapes and consequently be harder to train. Even though you might like to have an ansatz that's both highly expressible and trainable, you can't always get what you want. And one thing I'm just going to highlight is I've said right at the start, I was going to focus on just the talk simple costs where you just have one initial state and one measurement operator, but this bound completely and very straightforwardly generalizes to costs using training data. It just looks a bit messier on a screen. Okay, so we can't have an ansatz that's both expressible and trainable, but the upper bound leaves little room. Inexpressive ansatz may, but are not guaranteed to exhibit larger cost gradients. And this prompts a question: when/how can reducing the expressibility of an ansatz increase expressibility? That's not what I meant to say. When/how can reducing the expressibility of an ansatz increase trainability? So we decided to explore this numerically. And okay, what we did, we considered an ansatz of layered ansatz of this form. So we've got a layer of single qubit rotations. So each of these is either an X, Y, or Z rotation about some angle theta, different angle each time, at least in the first instance. And then we have ladders of ZZ rotations. And then the first thing we looked at was reducing the depth of the ansatz. And as entirely predicted by Marco et al. Results, for a global cost, this makes no difference. You're always screwed. Your variance in the partial derivative cost always vanishes exponentially. But for a local cost, actually reducing the depth of your ansatz really helps. It substantially increases the observed cost gradients. Second thing we looked at was correlating parameters. So the first thing we looked at was correlating qubits. So that is within a layer, all the qubits rotate by the same angle, but that's allowed to vary from layer to layer. Then we considered correlating layers. So each qubit rotates by a different angle, but it rotates by the same angle in each layer. And then we basically correlated everything, correlated qubits and layers, and just have everything rotating by the same angle. And what we find is that for a local or global cost, In both cases, this substantially increases the observed cost gradients. And finally, we considered restricting rotation directions. So instead of allowing these to be X, Y, or Z rotations, we considered them just being Y or just being X. And again, in at least the case of a local cost, this did substantially increase the observed gradients. Can we avoid these techniques to use a bound plateau? Yes, we might be able to use them to avoid a bound plateau, but can we use them and then actually still solve the problem successfully? Well, it's only going to work, at least straightforwardly, if the reduced expressibility ansatz contains a solution to the problem you're trying to solve. So generically, actually, these techniques may not be very helpful, but if you have symmetries in your problem, perhaps they could be helpful. So say you do have translational symmetry, perhaps actually correlating qubits might work. You might find that actually your less expressible ansatz can capture the solution, potentially. Failing that, these are more likely to prove useful in a perturbative sense. So you might do something like initially reduce your circuit depth, initially correlate parameters, initially restrict rotation directions, try and hone in slightly on the area where your solution is, and then slowly increase the expressibility of the ansatz by decorrelating parameters so you can capture the solution. Potentially you can play around with things along those lines, but it definitely requires more research. Okay, so the punchline is your ansatz cannot be both expressible and trainable. And it looks like that it's going to be expressibility that we're going to have to sacrifice. And that's because the crucial thing to notice is your ansatz does not need to actually be expressible, highly expressible in order to work. So this inexpressive ansatz I showed earlier actually would work perfectly well for problem A. All you need is that your ansatz contains solutions to the problem you're actually trying to solve. So what we want to do is actually come up with good problem-inspired ansatzer that well explore the space of solution unitaries, but don't explore the space of the whole space of unitaries. So they're inexpressive, but complete. Easier said than done. Yeah, I definitely, job for the future is going to be to come up with good problem-inspired quantum neural networks, good problem-inspired ansatzers, and or perhaps perturbative techniques that I touched on in the previous slide. Okay, but even if this is possible, there's another trainability roadblock. Certain problems are untrainable, no matter what clever strategies you employ. And that is what I'm going to briefly move on to discussing in the much shorter second half of my talk. Okay, but before I get there, to just add some colour to the final result I'm going to share with you and sort of illustrate it slightly, I'm just going to take a step back and recall the Hayden-Preschool thought experiment. So in this thought experiment, Alice throws her diary into a black hole. Alice's secret diary, of course, is encoded in a quantum state, because what else would you encode it in? And the question is, can Bob recover it? Well, given that black holes are nature's fastest scrambler, and scrambling is the process by which quantum information gets rapidly spread throughout many body systems, you might have thought that it would be pretty unlikely. But actually, Hayden and Prescott argued that if Bob knows the unitary dynamics implemented by the black hole, then actually, yes, it would be possible to decode and recover Alice's secret diary. So this prompts the question, well, how the hell would Bob learn that unitary? Well, what we've shown is not using quantum machine learning, not by training a quantum neural network. So scrambling, as I said, is the rapid spread of entanglement and information through many body quantum systems. And it's not just important to black hole physics, it also has applications to a wide range of other areas that I don't have time to discuss, including quantum information theory, thermalization phenomena, random circuits, fluctuation relations, and more things I don't have space in my slide for. So it's important to a wide range of physical phenomena. How do we diagnose it? Well, one good way of doing this is through the use of OTOCs, so out-of-time ordered correlators, such as this one that I've sketched on the right here. So here, X and Y are local operators acting on different subsystems. So for example, they could be Pauli operators acting on different qubits. X tilde is the time-evolved initial operator. So it's the initial local operator evolved under the unitary that you're trying to figure out whether or not it's scrambling or not. And then what you do is you take their commutator, effectively square it, and then take an average over the infinite temperature thermal state. So just a mixed state. Okay, so the OTOC of a scrambled system decays rapidly. The OTOC, when B is a highly scrambling unitary, takes a small value. How do you see this? Well, if B is identity, then as X and Y are local operators, they're going to commute, and your OTOC is just going to be 1. But if V is highly scrambling, then your local operator is going to be taken to a global operator. Your X tilde and Y don't commute, so this term is larger, so the OTOC is smaller. Or more concretely, as shown in this nice paper here, the OTOC of a scrambled system takes a minimal value that is equivalent to taking its average over a random distribution of unitaries. And this means we can model a scrambled unitary as a typical random unitary. But notice actually that this here involves only 2 copies of V, so only 2 copies of the unitary you're trying to quantify. And so that is, we can actually model a scrambled unitary as a typical pseudo-random unitary. So we can model the OTOC. The OTOC of a scrambled system takes a minimal value that's equivalent to taking its average over a distribution of unitaries that agrees to the random distribution at least up to the second moment, i.e. a form plateau design. So yeah, we can model a scrambled unitary just as a 2 design. Okay, so then the question we want to ask is, can we use a quantum neural network to learn a target scrambling unitary? What? Got to get that. It's got like 3 minutes. Okay, so you could ask whether you can do this using a compiling cost of this form, the one I introduced earlier, or you could actually ask whether you could do it using a slightly more general compiling cost that allows for entangled training data, or potentially even using distributive quantum neural networks. So that's what we investigated, and what we showed is that if you try and use such a compiling cost to train a quantum neural network to learn a scrambling unitary, which we model as a unitary on Form 2 design, then we find that the average cost gradient vanishes, and also that the variance in the gradient cost vanishes exponentially. And so this means if you combine it with Chebyshev inequality, what you can find is the probability that the gradient cost is non-zero for a typical scrambler vanishes exponentially with the size of the problem. And now, crucially, this result holds for any choice in ansatz, and so this acts as a no-go theorem for learning scramblers using various quantum algorithms or quantum machine learning. No matter how hard you try, you're going to get stranded in a barren plateau and not be able to train. We just performed some numerics to illustrate this. So in these numerics, we use the minimal model of a scrambler introduced by Swingle et al. So this allowed us to model approximate scramblers. I'm not going to go into details about it, but essentially this G parameter acts as an entangling strength, and this T parameter is your scrambling time. So for large G and large T, you're dealing with a highly scrambling unitary. In this case, we find that the cost landscape, so here we're plotting a cross-section through the cost landscape. The landscape forms a barren plateau with just a narrow gorge where the cost dips down to a minimum. In contrast, for weaker scramblers, so short T, small g, then the valley is much wider and the plateau more featured to allow for training. Right, okay, so what have we shown? We've shown that barren plateaus are exhibited by scramblers. So that is, if you are trying to learn a typical scrambler, the variance in the cost gradients is going to vanish exponentially. The probability of observing non-zero cost gradient is going to vanish exponentially, and you're going to come up with these very, very flat cost landscapes. More generally, because we modeled a scrambler as a typical pseudo-random unitary, our result also applies for learning typical random unitaries. That is, you're also going to exhibit a barren plateau if you try and learn a typical random unitary. So in this sense, randomness seems to be a barrier to trainability, which in the first instance sounds a little bit worrying. But I think sort of thankfully, luckily, most sort of physically interesting processes that we're going to want to try and learn are sufficiently simple or sufficiently structured that they don't resemble typical random unitaries. So in this sense, this doesn't really sort of condemn quantum machine learning or variation quantum algorithms, but rather sort of puts a limit on its domain of applicability. But yeah, take-home message is there are fundamental limits to quantum machine learning, and maybe we're going to need to put more thought into what types of systems can and cannot be learned. Right, and I was just going to end by flashing up this overview slide again, summarizing what I've been discussing, and I look forward to the questions.
Thank you so much, Zoe. Fantastic talk. I'm going to just jump in with a quick question, and your last slide is really appropriate for this. Actually, even though there is, of course, a trade-off, as you have explained very eloquently, between expressibility and trainability, in the classical case, it seems like it's possible to have very expressive, high-performance models that are also trainable, right? So can you comment on to what extent that trade-off prevents both things from being realized? And do you think that there's something special about the quantum case that may or may not give us hope that we can also achieve something similar to what happens on the classical side?
So one thing, I don't know whether this answers your question, but barren plateaus are much more of a problem in the, they're very different in the quantum context to the classical context. So vanishing cost gradients are not so much of an issue in the classical concept because we don't have precision limitation in the same way. You don't have to evaluate your cost function using many, many shots, so it doesn't become very resource intensive to get gradients. So in that sense, I think barren plateaus really are more fundamental in the quantum regime than classical. And so, of course, then the trade-off is going to be more fundamental in the quantum regime than classical.
Okay, gotcha. And then you alluded, of course, to the need for further research to address these issues, right? Could you elaborate a bit more on this? Do you have any insights, any ideas of what more exactly can we do to tackle these challenges?
So I think this one's the really important one. Is how do you come up with good problem-inspired answers? And I think actually, so to some extent, Marco's talk on Monday touched upon this. So a lot of trying to come up with whether or not your ansatz is going to be trainable or not can be ascertained through looking at your Lie algebra and sort of the symmetries of your problem. So I merged together two different thoughts there. So you can use ideas from control theory to try and assess whether or not your ansatz is going to be trainable in advance, and I think that's an important strategy to employ. The other thing, and it's sort of related, is you're going to have to try and come up with, you're going to have to use the symmetries of your problem. You're going to have to use physics to come up with what's a good ansatz. So if you're studying, okay, easy one, sort of VQE for some system with various translational symmetries, various particle number conserving symmetries, things along those lines, you're going to want to try and build all of those symmetries into your ansatz. And so reduce the expressibility while also hopefully capturing some of your solution space.
All right, perfect. Zoe, maybe in the interest of time, switching gears a little bit, we have a lot of questions about researchers' trajectories, right? And you very recently landed a faculty position in Switzerland. Maybe could you share a little bit what the process was like?
Of applying, or
of applying, and also like how you felt upon receiving the news.
I mean, it was crazy. I mean, it was more work than I thought it was going to be. I hadn't applied for a faculty position before, and I didn't really appreciate how much time and effort it would take up. But I really enjoyed actually having the time to sit down and think about what I wanted my overall research strategy to be over the coming X years. Then trying to actually find the words to describe that. And one thing that made clear to me is I sort of hadn't realized, so I'm particularly interested in trying to get quantum computing to work out for physicists. Like I'm not as interested in sort of, Well, I do like, this was a more foundational talk talking about sort of fundamental limits of quantum machine learning. But I also like to sort of, and I like to have that rigor, but then I also like to take it and like try and apply it to real physics problems. I am not going to be someone who ever does quantum machine learning to optimize shipping forecasts or whatever it is. Like, I don't know, shipping to, you know, you get the financial prediction QML algorithms. That's never going to be me. And then the interviews were fun. Talking to lots of future colleagues, trying to package up my results in a interview style presentation and that kind of thing.
Nice. Well, thank you for sharing that. You know, for the audience, when we give a questionnaire to speakers, and one of the questions is there something you're a fan of? So Zoe wrote the following, and I actually checked with my colleague Paul, who's into climbing. She said that she's a fan of mono undercling thumb sprags. I repeat, mono undercling thumb sprags. I believe this is supposed to be a joke. But
I was procrastinating from a referee response I really didn't want to fill in that day.
That's a great response.
My slightly facetious answers. What did I say? It was monocling thumb sprags.
Mono undercling. But Zoe, basically, can you tell us about you know, the adventures you have while climbing and kind of that side?
I will tell you what a mono undercling thumb sprag is first.
Let's do it.
It's a hold that you can just get your thumb in, kind of in that position. And what's really satisfying about it is most of the time you're climbing in your fingers. And then if you find a hold you can use your thumb on, it feels slightly unnatural, but it gives your fingers a break. And it's just really satisfying that you can actually rest just off one thumb. So that's why I like them.
Oh, I see.
But yeah, climbing's my main thing. I sort of work hard in the week and then spend most of my weekends climbing, a mix of sort of sport climbing, and then if the weather's up for it, trying to get up higher up into the mountains, doing a bit of trad. Oh, I'm also liking being out here and getting to do sort of desert cracks. That's fun too.
Oh, wow.
I had a Indian Creek the other day.
So do you have a particular highlight of your climbing experiences that you want to share?
There was a route called Wolfgang Gulich in Sardinia. And maybe I shouldn't confess this live on air, but it was
or maybe you should.
route that I'd ever tried to do in my life at the time. So I think it's something like 13, 14, 15 pitches, 7A, bunch of 6C pitches. And I did it the same day as my flight home when I was meant to be working the next day.
Oh, wow.
And I thought there was a very good chance of missing my flight. And I wasn't too sad about that because I was really enjoying Sardinia. But then somehow everything just worked. Everything worked. Everything went to plan. Everything went smoothly.
Oh,
I
bummer.
managed not to miss my flight and back to work the next day.
That's a good one. And Zoe, and I warned you about this. I really have to ask. You also mentioned some of your escapades in competitive eating. I think we have a great anecdote about this, about resilience, and maybe.
I think the competitive eating part is. I mean, yes, it is what the story's about, but it's more that I'm not very good at losing.
Well.
Or no. Or just right, I'll show them. So yeah, I was. This was a pub quiz with my family when I was a teenager, and the way it worked, you had to nominate someone from each team to go out to the front, and then once you were out the front, they were assigned a challenge, and all the teams had to basically bet on who was going to win. And I was volunteered, it was my turn, and then I was up against a bunch of other big guys, big teenagers, big men, and I was like a 12-year-old girl who was half their height. And it turned out the competition was who can eat the most biscuits. No one, of course, voted for me. They all voted for the big guys, and I thought right, I'll show them. And somehow, actually, I managed to win the biscuit eating competition.
I love to hear that.
There's evidence of my stubbornness.
And your skills as well. And underestimate Zoe at your own risk, is what I will say.
What was that?
Underestimate Zoe at your own risk.
Yeah, just don't place a bet against me, because I will go to extreme lengths. Then to try and prove you wrong.
I will place a bet against you being able to show to solve all the problems you mentioned in the talk. How about that? Maybe I can get some inspiration. Zoe, anyway, we have some questions from the audience. This will more pertaining to your talk, so we're going to switch it back. So Quantionomeli is asking, so what are the assumptions for applying the upper bound of the variance that you showed in the first part of the talk? And is this formula general for any ansatz?
So the thing to go back to is this expression.
Yeah, so maybe we want to show the slides on stream. Just keep going, Zoe.
Can you okay, cool. So this is the type of ansatz we're seeing. So you've got alternating layers of fixed gates and parameterized rotations, where the parameterized rotations take this form. Bj is emission, Bj squared is the density, and we assume that these angles here are uncorrelated. And we've got a cost of this form. So that's the assumptions for the bound I showed earlier. And we've also got a generalization for the case where essentially we have a sum of a bunch of terms of this form.
Okay, thanks for asking. We had a bit of delay sharing the slides, but I think it's okay. And maybe one final question. Are there systems that can be learned? So let me rephrase the question. So it's a question about the work that you'll be pursuing in the future as part of your new group in Switzerland. And as the question is, are questions regarding things that can and cannot be learned? I think this is maybe arising due to the notion of scrambling. So kind of you could argue that what's happening there is like this looks very difficult to learn, right? So I think this question is asking more generally, is this a direction that you're still willing to pursue, to ask questions about what can and cannot be learned in a quantum setting?
Yeah, so one thing that I think would be interesting, so I want to try and, okay, even though I said that this is a no-go theorem, so I'm trying to get out the right slide. I was trying to figure out which slide I wanted.
Okay.
So even though I say this is a no-go theorem, I am interested in trying to figure out ways around it. So for example, if you're thinking about a scrambling system as a function of time, at short times it is only a thermalizing system, and then it becomes a scrambling system at later times. So at short times it will actually only form a one design, and then at longer times it forms a two design. And the no-go theorem only kicks in at longer times when it starts to form two design. Mm-hmm. So you could potentially learn its short time dynamics when it only forms a one design. And then I'm wondering, could you then kind of sew it together? Could you learn short chunks of time, and from learning the dynamics at short chunks of time when it is learnable, then sew it together and get perhaps not its entire long time behavior, but some aspects of it? Or could you sort of learn coarse-grained aspects of its behavior? So you might not be able to predict all its properties at long times, but maybe you'll be able to predict some properties at long times. So things like that I'm interested in investigating.
Nice. Certainly very interesting. Zoe, unfortunately, that's all the time we have for today. Thank you so much for joining us. Really appreciate it. Another fantastic talk. And I wish you a great rest of the day.
Cool. Thanks for having me.